Now let's do some useful theorems in this theory of series. The first one is harmonic series diverges. Now this is the series that we call as a harmonic series, right? So it's like it's a normal series, but we give a special name for this particular one. That means if we have this sequence, right, and if we consider this sequence, and if we take the summation of the terms in this sequence, that means this one. So if we write down the terms, I mean the first few terms, it will be 1 over 1 plus 1 over 2 plus 1 over 3 likewise. Okay, so here the theorem says that the harmonic series diverges. Now this sometimes this is kind of a surprising result, right? Now the reason is, now you can see that this sequence, the sequence of the terms in the series will converge to 0, right? The limit of an, that means the limit of 1 over n sequence is equal to 0. But we can prove that when you add up all these terms, then the sequence of partial sums will diverge. It actually goes to infinity. Okay, so this is kind of a very surprising result, because although we add numbers, it will be like when it goes to this far end corner, it will be like very small numbers that we are adding. Okay, because now the sequence of an terms going to 0 means this is actually a decreasing sequence. So the value of the sequence points will be reduced gradually, and it will converge to 0 in the infinity. Okay, so the physical value of each and every term when it goes to this right hand side is very small, but this series being diverges means although the number that we are going to add is very small, the series will be infinity, like it will converge, or in other words, this summation will be a very large number. Okay, like number in the sense it is infinity, it is not a real number, or it is greater than all the real numbers, right? That's what we call, like, that's the meaning of infinity, right? So now here I did not mention the proof of this one, okay, and I am not going to discuss it in here because the calculation is a bit tedious, right? So I am not going to discuss the proof of this one, but it's worth remembering this result. Okay, the harmonic series diverges. Okay, so now normally when I say diverges, it will count for both cases where the limit of this partial sum sequence is infinity, as well as for the case where the limit of the partial sum sequence does not exist, right? Like for the cases like, can you remember previously we had a situation where we got the partial sum sequence as this one, so it does not converge to any point. But if we have a partial sum sequence like this, like increasing one, it will go to infinity. In both these cases we consider as a diverging situation, and in both these cases the corresponding series will diverge, right? So anyway, here what will happen is, if we go through the proof, you can see that the partial sum sequence will go to infinity. So anyway, we can say that the series diverges. So it is very important that you remember this series. This is called the harmonic series, and that series will diverges, right? And don't mix these things up, right? Now this sequence goes to 0, right? This sequence will go to 0, but the partial sum sequence obtained by this series will go to infinity. That is why we say that the series diverge. Okay, right. And the second theorem is, if the limit of an is not equal to 0, then the series an diverges. I will explain this with an example. Okay, so let's consider this series n squared 5n squared plus 4. Okay, so if we take this series, now here the an sequence, that is, we can even represent the same series like this, right? So the an sequence will be equal to this term. The nth term of the an sequence will be this one, right? So our an sequence will be this one. Now remember, this is not the partial sum sequence. Okay, this is not the partial sum sequence, right? But this is just the an sequence. And the theorem says, if the limit of this sequence, that means the limit of, now for in our particular example, the limit of this one, and if this is not equal to 0, now let's see what is the value of this limit. So to calculate the limit, since it goes to infinity, we just have to take out the largest power from both numerator and the denominator. So these two will get cancels out, and the answer will be 1 over 5. So you can see that the limit of an when n goes to infinity is equal to 1 over 5. That means it is not equal to 0, right? See, in the theorem it says, if the limit is not equal to 0, then the series diverges. So because of this reason, and from that theorem, we can say that the series diverges. Okay, and here you have to be very careful when using this theorem. Okay, because it only says what happens if this is not equal to 0, right? And what about this one, 1 over n? This is the harmonic series that we discussed, but you can clearly see that the an sequence, which is 1 over n, and the limit of an is equal to 0, right? But having this condition does not say anything about the convergence of the series, right? Because now this theorem says, if it is not equal to 0, then it diverges, right? But if it is equal to 0, we cannot predict anything about the convergence or the divergence. Okay, it can be converged, like it can be a convergent series, or it may not be, right? And we, in the previous theorem, we specifically mentioned that this series diverges, right? So this is a good example where you have the limit of the sequence going to 0, but the series diverges, right? So, and I will repeat this once again. This theorem only says a result when the sequence an, and this is not the partial sum, when the sequence does not go to infinity, it does not go to 0. If it does not go to 0, then the series diverges, right? And I'll do another example. Let's take this one. N equals 1 to infinity. Now, in a previous video, we considered the partial sum, the sequence of partial sums associated with this given series, and we saw that the sequence of partial sums was something like this. Okay, so this did not converge, so we concluded that this given series also diverges, right? But instead of going for these partial sums, we can even use this result to prove the divergence of our third series. That is, now according to this series, our an sequence will be -1, +1, -1, +1. Okay, and here once again you can see that the limit of an also does not exist, right? So in other words, you can say this is not equal to 0, right? Because for this to be equal to 0, the limit should exist in the first place, right? And this even does not exist, right? So from the theorem written in the green color, you can again say that the corresponding series diverges. So here we have the divergence of this series, right? Because you have the sequence an, because the sequence an is not convergent. Now we have done two methods to prove the divergence of this particular series. And also we can rephrase the second result, this one, like this, and it is called the transposition of a if-then statement. Now this result is also correct, okay, but the previous one is the most useful way of looking at it. But anyway, you can even find this statement as a theorem, right? It's like it is obtained by rephrasing the previous result, okay? That is, if a certain series converges, then the limit an is equal to 0. So in other words, if this is not equal to 0, then this cannot converge. But it is not the other way, right? This being equal to 0 does not imply that the series converges, right? Now this does not imply that the series converges, but limit of an being not equal to 0 will imply that the series diverges. So we cannot use, now you can even consider this one or the second, the result that I wrote previously. That is the most that is the most convenient way of looking at this result. So anyway, what I want to highlight here is that this above result does not help you to identify whether a series converges. It is helpful only to identify whether it diverges, okay? Because we cannot say anything, predict anything about the convergence, because this being equal to 0, we cannot say anything about the convergence, okay? But if it is not equal to 0, we can definitely say that it diverges. So we normally call this test as a test for divergence, not for convergence, okay? Because from this test we can only make a conclusion about the divergence, and so please do not use it in the wrong direction, okay? It is only useful when it is not equal to 0 and in this direction. So it will be helpful if you can remember this result, right? Now here, this is a diverging sequence, this is a diverging series, but the sequence goes to 0. Okay, so but still this diverges, right? So in our theorem it says an, if it is not equal to 0, if it doesn't go to 0, then the series will diverges, right? Okay, and as the last theorem, a familiar result, right? Now here we have, like, if you have two series an and bn, and if they are convergent, if we multiply a convergent series by a constant, then the resultant series will also be a convergent series. And also you can write the things like this, right? Say if we have now we know that this series, we proved that this series converges to 1. Okay, and if we multiply the series, let's say by 10, right, we can then take this 10 out from the sigma notation and rewrite the series like this, and we know the answer for this one is 1. So the total answer will be 10 times 1, which is equal to 10, right? And we can only do these stuffs if we know the initial, this basic series, if we know this basic series is convergent only, right? Then only we can do these things, right? And to support with the second statement, just consider the two series, this one and this one. Okay, so this is our an and this is our bn. We can show that both these series converges, right? Well, actually we have already shown that this series converges. Remember, by taking partial sums, we proved that this series converges, and it converged to 1. Okay, so this series 3 times that one will converge to 3 times this series, so that will be equal to 3. Okay, the answer for this one is 1, so the total result will be 3. So the answer for this one is 3, and this one we already proved that it is equal to 1, right? So the addition of an plus bn will be equal to sigma an plus sigma bn, and that is equal to 1 plus 3, and the answer is equal to 4. So now simply what you have to remember is, if the two series are convergent, then they are very easy to handle, right? But if one is diverging, then we cannot say anything about the summation or this constant multiplications, right? Because then it will not make any sense, right? So these are the basic tools that we need in the theory of series as well as the sequences. So please be thorough with the content that we covered during this week, because it will be very helpful when you are learning some further mathematics, right?